And welcome to Robotics here in the beautiful State Capitol building on this wintry April day. And we are so excited to be able to bring what we think is kind of like bringing Star Wars to the Capitol building. It was amazing to see a robot and a drone enter as we came in the doors today. And to introduce our University of Michigan robotics team is none other than State Representative Yousef Rabhi from the great city of Ann Arbor, go blue. And Representative Rabhi is on the Appropriations Committee. He is going to be leaving us to go back to appropriations, but he took a moment to come and greet you. So without further ado, please join me in welcoming State Representative Yousef Rabhi from the 53rd District.
Well, it's an honor to be here with you today. It is still morning, right? Just barely. 2 more minutes of morning left. So it's an honor to be here with you this morning. Thank you for inviting me to come and address this group. I am upstairs, just above here, in Appropriations Committee, and they're talking about the insurance budget. But I figured I would pop out and just introduce myself and greet you and welcome you to the state capitol. So I'm a U of M alumni, graduated in 2010, and go blue. Thank you for the applause. I graduated. It was like almost 10 years ago now. I'm feeling kind of old. But you know, this is a really important group. The Wolverine Caucus is an amazing organization of people that have come together and talk about important issues here at the University of Michigan. But as it turns out, many of the important issues that we have at the University of Michigan are important issues to our whole state and frankly to our whole nation. Because the University of Michigan is a world-class institution, is an institution that does work like in its robotics program that transforms the conversation not only in our state but across our country and across our world. We're doing some really innovative things here, and I wish that I could stay and learn more about what the robotics program is doing at the University of Michigan. But I'm sure that you are going to be blown away by the phenomenal progress that this program has made over the years. They're doing some amazing things. And Cassie Blue, is that the road? Cassie Blue. Cassie Blue is one of my favorite constituents. So I've seen all the YouTube videos, you know, a lot of progress has been made. And I tried to get a pass for Cassie Blue to come out on the floor of the House with me, but we are going to be introducing her from the gallery today on the floor. So looking forward to having you, Cassie Blue, in the House of Representatives. So thank you to all the students that have worked tirelessly on these programs. Thank you to all the teachers, professors, faculty, and staff who have been part of bringing this together. And thank you to all of you for your interest in coming here today to our state capitol to celebrate our robotics program and our wonderful University of Michigan. Go Blue.
So first up, we're going to do a couple of talks today, and we're going to talk about drones, we're going to talk about Cassie, we're going to talk about the Robotics Institute, and we're going to have one of our student teams talk about their autonomous vehicle. But I'd like to introduce Professor Ella Atkins. Ella has been part of the steering committee for robotics since the beginning. She's a professor of space engineering. She's also our grad chair. She wears about 19 different hats, but today she's going to be wearing her drone hat. So Ella Atkins, please.
First, I want to say I'm not going to stay at the microphone, so I apologize in advance for that. I'll talk really loud, though. So in the job of wearing my drone hat, I brought a couple of toys, and I'm showing you a slide in our exciting new test facility in Air. So one of the things that happened several years ago when drones first started to become popular is FAA said, not in my airspace, and we said, wait, we have a lot of education and research activities. So things happened over the years, and at this point, it's not too hard to get permission to fly outdoors. But at that point, we asked the question, wait a minute, we have 18-year-olds who think they're invincible and have a lot of cool ideas. What do we do to make sure that they actually are safe, regardless of policy? So one of the responses to that was that the University of Michigan, which is very exciting, decided to build a netted flight facility. So you're seeing this flight facility at night, which lets you see that it has lights. You see mud on the ground, it's going to have grass really soon. But the idea with this is that it's a 50-foot tall, 80-foot by 120-foot volume that is right in the middle of North Campus. It's next to the Space Research Building across the street from the FXB, and it's going to be adjacent to the new robotics building. So what this means is that anybody who has any ideas that they want to try out can just go out the door, go into this net and try them out without any fear whatsoever that they're going to injure anybody as long as everybody stays outside the net. So that's what this is. We fly drones like what you see on the table here in this facility. Obviously, larger fixed-wing aircraft would be hard to fly here, but we do have some small hand-tossed fixed-wing aircraft that we can fly in here. We're going to be offering a new experimental UAS unmanned aircraft systems class in winter 2019, which is one of the hats that I'm very happy to wear. It's probably my most fun hat over the next few months. So I'm now going to walk away from the microphone and point to drones and then show a short video, and then I'll be done. This particular drone started with a $20 Amazon kit of pieces and was augmented by a graduate student to do research. On top is a BeagleBone Blue, which is an embedded computer board running Linux, which is capable of doing anything from processing sensor data all the way up to executing advanced algorithms that automate or make autonomous this platform. The prop guards that you see here were 3D printed. One of the reasons we have them with these motion capture targets is to allow us to both operate indoors and outdoors without anyone putting their fingers through the propellers, or without these vehicles hitting each other and tangling their propellers with each other. This particular platform is going to be used this summer with many just like it to do what we call cooperative aerial transport, which means we're going to have several of these attached by ropes to a common payload, and they're going to autonomously carry that payload from point to point. The application of this is in supply delivery in disaster zones. Right now, you have to take a giant helicopter that itself is pretty dangerous and might or might not be able to land in an area that's been very impacted with debris and so forth. If you have many of these small vehicles, they pose much less risk than a giant helicopter, and they can still carry a large payload once we solve the challenges of having them autonomously able to do that. Once we get motion capture perfected with controllers, we'll pull that off. One of the great things about this test facility is that we can go out in all of the wonderful Michigan environmental conditions and make sure that we can still fly safely and find the cases where we can. This big vehicle was one of the first quadrotors we had in robotics, designed by a company called SkySpecs, which is a startup of University of Michigan students after they graduated. At this point, they're mostly focusing on wind turbine inspections, and they moved past this vehicle to vehicles that are off the shelf. We still use their quadrotors in our Robotics 550 class, which is a lab class, the first class that our graduate students take along with the math class. What you see on the bottom is the Delta arms. Delta arms are used in factories for pick-and-place applications. They can, at very high speed, very accurately position their end effector and grab things. So what we had this vehicle doing was autonomously flying indoors using motion capture, because that didn't open until a few weeks ago. And they were asked to pick up blocks with this gripper autonomously, carry the block to another place, and deposit in a container. So this gave the students the opportunity to see the full system from the realization of the design. They all designed, manufactured, 3D printed, and built the Delta arms themselves, including the gripper. They tested those without the quadrotor in a lab, and then they automated the quadrotor without the gripper, and then they put it all together so that they had to coordinate the autonomous flight with the software. On the bottom is another BeagleBone, like you saw in the small one, that they wrote the software on, to autonomously grab, climb, and deposit blocks. So I have a short video showing some of the labs activity, and then I'll stop. But please, while the video is going in the background, feel free to ask questions, and then I'll stop. So this goes all the way out back to 2014, the first time we actually had a robotics program in place. We have a different project every term. So this is really showing the evolution of the students from a very early stage where things ever worked. In this case, they were designing a Delta R to pick up a ping pong ball as opposed to a block. So you can see this wooden base is a surrogate for what the landing gear looks like on a quadcopter, which allows them to basically just test the end effector. So this is them in the lab trying to convince the end effector to pick up a ping pong ball. Sometimes it dropped it. We had some Velcro on it to keep it from falling off, and so in this case it was picking up both the Velcro and the ball. Oh, oops. So one of the great things about this is that people know that it's possible to do these things. They know it's very hard. And it's amazing how determined these students are to actually see it through to completion. It makes them really willing to do all of the hard work necessary to learn about the software, the electronics, the calibration of sensors, the building of better mechanical components, and the realization of the whole system of everything put together. Any questions? Well, I'm happy to share this video or other slides with anyone who's interested. Please contact me. Yes?
What's your 3D printer? Is that something you use frequently to make parts?
Oh, absolutely. In our robotics lab, we have 4 or 5 of them, I don't remember which. And so the students will build a CAD file, basically a design of each part. And then we have the plastic. For a while, we only had base and blue plastic. It was kind of cool. So then the 3D printers are building. For example, these ducts are built in 2 pieces and then put together. So these are 3D printed. And then all of the yellow and green parts, I guess maize on the bottom, you see were 3D printed as well. So an important part of that is to get the people either with mechanical backgrounds just doing cool stuff, or the people with other backgrounds like electrical or computer science, they get exposure to actually designing and building a part. I think they find it a little more challenging than they thought it might be, because everybody thinks everything else is easy until they try. One more question? Yeah, go ahead.
You hear from Amazon, or do they participate in your research and learning?
Oh, so the Amazon what?
Amazon, do you hear from them, and do you work with them?
Yes. So I'm in the drone world, and as open and great as Amazon is with their robotics competition, they are exactly that closed with their drone work. They feel like they want to keep all of that inside. They want to do their testing in a proprietary way. So I wish them well, but I don't work with them. There are some companies that want to collaborate and be open, like Sky Spectrum University. Others kind of like. Thank you.
Thanks, Ella. So as he's getting set up here, I'll introduce our next speaker is Jessy Grizzle. Professor Grizzle is the inaugural director of the Robotics Institute. He is also a professor in electrical engineering, and he is the father of Cassie Blue, as well as a host of other robots, and he'll be telling us a little bit about the Robotics Institute today.
Excellent. Everybody can hear me just fine. Thank you. Thank you. Oops. Little VGA excitement here. It was there. It was alive. That's us. Okay, so I'm going to tell you a little bit about the Robotics Institute. So the history of it is in 2011, then Associate Dean for Research, Alec Gallimore, asked Don Tilbury to put together a steering committee to see what could happen if all the roboticists on campus got together and combined their efforts. Well, from 2011, that committee turned in a white paper which described a vision for the Institute. It looked at all of the other institutes existing in the country and what it would take for Michigan to actually become the #1 place to do robotics in the country, if not the world. 2013, a building plan went into the funding of the university, and in 2014 we opened up the graduate program that Professor Atkins was just talking about. So things happen fast, okay? We had the groundbreaking for that just last Friday. So, you know, when you think about Robotics Institute, you're thinking about machines like Cassie Blue, etc. But when I'm done today, I hope what you're thinking about at Robotics Institute is people. Because it's really people who do all of the exciting things. And the whole institute is built around getting people working together. And so what we're always trying to do is have fun working together. Yes, we make these really amazing machines and the software and the brains that go in them. But we want to build devices that help all of us in society. So I had the great pleasure of being able to take over the ground laying work for this institute that Professor Dawn Tilbury did. She is now Director of Engineering at the National Science Foundation. Okay, so I'm just telling you about the quality of people I get to work with. It's amazing, okay? Ella Atkins, she was being up here telling you all about her famous work on drones. She was the inaugural winner of the University of Michigan Public Service Award, okay? Inaugural. That means you're taking the very best person on campus in the past 15 years who's working in this area. That's Ella. My executive committee, everyone on there won major awards at the University of Michigan this year. Okay, there's no other executive committee on campus that can make that claim. That's what I have. And then I have these amazing staff members, of which you've met Kimberly today, and Damon, who was being the MC. Thank you, Damon, for doing that. So these are the core faculty members in the Institute. So just take a look at us. There's 24 there, that's the big number. 8 of them are women, 3 are African American males. So I'm going to show you about 3 different ways that we are actually diverse in this institute in the way that we are thinking and the composition of our group. Okay, so one is just gender and ethnicity, so that's one important way. Now when you have that many people having fun, others want to kind of join with you, and so that's what we have with the core members plus the affiliates. So now when our students come, they know that they can go to the affiliates to get consulting in artificial intelligence, machine learning, mechanical equations of robots, vibration theory, all those types of things. So that's wonderful. But what I'm going to show you is another way that we are diverse, and this is what makes the Institute especially well placed to become the #1 institute of robotics in the country. And that's because most of the robotics institutes in the nation came out of a computer science department. And I don't really understand why. Maybe it's because the smarts people think is important, but the bodies of the robots are also very important as well. Okay, so we have people from aerospace, as you saw with Professor Ella Atkins, biomedical engineering, civil engineering, computer science, electrical engineering, industrial, information, kinesiology, mechanical engineering, marine engineering, medicine, and architecture. So that's a diversity of views on how you can create machines, but also how you can create machines that help people. Now we have a couple of other taglines that we associate with us. One of them is this algorithms in motion. And I don't know what that means to you. What I hope it means to you is that the algorithm part says, yeah, Michigan is really good in the theory and stuff like that. But in motion is that we're always implementing our algorithm on real machines. And so we've got several of them here with us today. One that's in my lab, and Ella had her drones that were also professional research machine, but also teaching machines, and we have some of our student groups with us today. The other one is, how many robot videos have you watched that have 8x up in the corner? It's because you'd be bored to death watching it at regular speed. So our objective is for you to have 0.5x in there, or 0.2x. If it's 1x already and it's fun, it's good, but you should almost have to slow the robot down to see what it's really doing, okay? So we want robots that can keep up with us as people and you as society. The full spectrum thing is another way that I think this institute is super special. So it's got a couple of different ways. So one of the axes is we have robots that fly, we have robots that swim, we have robots that roll, we have robots that walk on legs, we have robots that slither like snakes. I don't know what else we have. We've got robots that can go to Mars, we have robots that are for the Earth, okay? But then the full spectrum part is, if you're really going to do robotics well, you need to understand all of the sensors and perception that a robot can perceive its own internal body in the outside world. You need people who are working on the hardware to make the bodies. You need people who are doing the local control algorithms that can move and interact with its environment. And then you need the higher level stuff, the stuff that scares you, the artificial intelligence, okay, that is allowing the robot to plan higher actions. And so for us, a higher action of a robot is what your toddler can do when it can go from one end of the room on another, crawling on its knees to get the ball to play with, okay? We'd be thrilled with that robot doing that, okay? So AI is not anything to be afraid of today. And then we're always doing things to help people and society. So this is just a kind of a collage of some of the different areas. When we start at the bottom here, rehabilitation robotics, we have really strong groups designed this presentation. Where you got your clicker? Yeah, there it is. Goes with you. Where you're from. How'd you end up in Michigan?
Yeah, so I'm a PhD student currently. I came from Louisiana, so I did my undergraduate degree at the University of Louisiana in Lafayette, where when I was an undergrad, I had an opportunity, like Jessy said, to participate in a IEEE robotics competition as part of my senior design project for my undergraduate degree. And I love that so much, I kind of just decided that would be my life direction, is to continue work in robotics. And kind of why I came to Michigan, because it's, I had the opportunity of kind of coming in as one of the first PhD students in the program. So I started back in that first class in 2014. So yeah, so this is kind of a collection of all of the PhD students and master's students that are currently working in our lab, working on control algorithms, state estimation techniques, and other things like that to make legged robots walk. So we get a lot of questions, and the first question we get is, why do we work on biped robots? Why not work on robots with 4 legs or 6 legs, or even wheels? And this is a perfect example of a scenario where a wheeled robot would probably not be the best idea to tackle terrain like this. And ultimately we want robots to go up mountains, up stairs, up ladders, and things like that. So wheels would have a hard time with that. Another reason we do biped robots is, in particular, is the world around us is really designed for humans, because our homes, our factories, everything was designed around humans. So if we can design robots that look like humans, they should be able to go into all the places that humans currently can go into, such as factories. And kind of a good example of this is during the Fukushima disaster, the nuclear disaster. The first robot to show up was a PackBot, a wheeled robot, and it took a week to learn how to walk upstairs. So if we had capable biped robots that could easily walk upstairs like humans, a lot less time could have been spent. Another reason we work on bipeds is we have the opportunity to help people. A lot of the research we do extends very nicely to exoskeleton work, such as here at this company, startup company Wondercraft that we're collaborating with. And also, a lot of the stuff translates really well to powered prosthetics. So this is a faculty member at UT Dallas who's used some of the algorithms that we designed and developed in our lab and kind of implemented them on prosthetics. And as you can see here, if the subject was wearing know, pants, you probably wouldn't even be able to tell that there was a prosthetic leg underneath that. And of course, because it's fun, we have lots of people. You can see young kids coming to learn about robots. It's a blast. There we go. So here's kind of a collection of robots that we worked on in our lab over the past years. And so our approach for controlling these robots is we like to use what's called the full order dynamic model. So essentially, we're creating a really intense mathematical model of the robot that describes all the interactions of all the joints and how much each link weighs and things like that. And we use math and physics to model these robots. And once we have this model, which we can start using different algorithms to design controllers that use these models to allow the robots to walk and maintain balance. So this kind of shows you some of the math. For example, for a very simple robot, you kind of zoom in here. This is the equations of motion describing how the robot can move. And you can see this is, tens of pages of really fine font equations. This is not anything that a human really would derive. And when you get to these complicated robots, we have to actually use computers to help model the dynamics and the physics of the robot. So we really leverage computers to our advantage to be able to help design controllers to allow these robots to walk. And of course, we really study the mathematics and the algorithms behind walking. Because we're interested in algorithms that are general. We don't want something that works on just one robot. We want something that works on a whole class of robots, between exoskeletons, power prosthetics, four-legged robots, two-legged robots, etc. So we're trying to build this kind of recipe so that other people can use on their robots. And this kind of gives you an example. So this is our previous robot, Marlowe. You can see another student in our lab, Dennis, doing some pretty extreme kicking tests to test how stable the robot is. So we're trying to design our controllers so that it can withstand these large disturbances and stay upright. You see here it adapting the kick to stay upright. And of course, we like to take our robots outdoors. That's where you really get the challenge of unknown terrain, and you can't really plan everything outdoors like you can in the lab. So this is kind of really proving ground for robots. We got Cassie Blue in August this past year, and we had it walking 6 weeks later. And so this is video footage from Associated Press who came and did shot some video outdoors. So again, we like to take Cassie in lots of different scenarios. Here's Cassie walking in rain. The robot is water resistant, so we did have to have an umbrella. And of course, because it is Michigan, we do take the robots out in the snow.
You can see Michigan Stadium from there. Way away.
And some of the future stuff we're trying is trying to put robots on segways, seeing if we can have Cassie control the segway. Some preliminary results from that. So kind of in the future look for more videos of this kind of work. So I think I get in there and do the demo. It works.
Should we take her to the front of the room? That's where the camera's going.
That's it.
Doing live demos is really stupid. is much easier just to show video. But the robot caught on fire. An hour later, these brilliant students had it out working again. Okay, so she weighs about 65 pounds. She's 35 or so inches at the hip here. What joint do you think that is? I'm setting you up, right? It looks like a knee, backwards. No. It's modeled off of essentially an ostrich. It's a slightly different bird for it. So that's actually the ankle. And you got toe joints down there. The knee is actually here, and then here's the hip. It's a very bizarre, but our mathematics doesn't care. So that's the whole point.
So yeah, as you can see now, Cassie's standing. So the motors are all powered on, otherwise Cassie would just fall to the ground. There's 10 motors in total. And we basically have a set of sensors that we're reading in all these sensor measurements and using that to calculate what
you can film
what torque commands to send to each motor at what time. So,
go big, Cassie, go big or go home.
So I have a radio controller here. I'm just giving high-level commands: turn, when to walk forward, when to walk backward, things like that. But all the balancing is done on a computer internally to Cassie. Yeah, so we give an approximate kind of speed command. So.
We are trying to fund our research program, so for a mere $5, you can come up with a selfie with Cassie. Just kidding, it's free. But we'll have the power turned off, because we don't want to pay medical bills, okay?
Got running batteries?
Yeah. It has a lithium-ion battery in the kind of in this front part here. It can last about 4 hours of walking.
Think she can walk down the aisle?
Let's see.
And then we'll conclude the demo. The first bipedal robot to walk down the aisle, folks. Oops.
Members, we're going to tell you a little bit about development applications. So we started out in 2016. Excuse me. So today we have autonomous vehicles that have traveled over 10 million miles. We have robots that. So we have robots that have gone to the depths of the oceans, and as you clearly saw with Cassie, we have robots that are walking around. For us as undergrads, this is really exciting. Somebody I think asked earlier, how do we get interested in this? Some of us have high school backgrounds, and some of us get interested when we see things like these. So, when this happened in 2015, the university opened in M-City. I was a freshman back then. And M-City is a facility for testing autonomous vehicles. And with the Robotics Institute opening and the graduate program, the real question is, what do the undergrads do? So one of the ways we do this is by creating undergrad teams. And we're one of 6 robotics teams on campus that are primarily undergraduate focused. So the value we bring to the table, is we provide this educational experience to students across the board. We connect them to industry and we further the university's mission. And this can be done through participating in specific challenges, learning skills, and networking with companies to eventually go out and apply our knowledge out in the world. So, how we, sorry, so for us, the way we do that is by going to this competition this summer, the Intelligent Ground Vehicle Competition. It's a competition that basically underlines the 3 big pillars around autonomy. members, Jennifer, explained to a bunch of new recruits the software that runs our controls algorithms, how all that interfaces. And so when it comes to interacting with industry, creating this pipeline, we'll invite companies in to give tech talks. We'll bring in engineers and other folks to really talk about their work and what they're doing in industry. You know, whether it's designing a planetary gearbox and then applying that knowledge and taking it elsewhere, or interacting with the engineers, or doing career development workshops. Teams like these really help fill that gap for undergrads to continue forward. And then we also participate in demo events, where we like to share the work we're doing with other students in our campus, or just folks like, for example, Governor Snyder last Friday at the groundbreaking. It's a great way for us to show our work and really share what we're doing. And kind of, all of this wouldn't really be possible without our partners and sponsors. You know, we have support from academic units on campus. For example, the Robotics Institute, our CPC sponsors, and we've also got corporations that we're working with moving forward. So where does this all go next, right? Eventually, we really want to take this team on, moving forward, and the goal is in a couple of years to build out a two-person passenger vehicle that students on campus can ride around, whether you're studying late and need to ride home, or you need to get something picked up from the grocery store. We feel this is a great way for us to really apply our knowledge and give undergrads an educational experience, so they can be prepared for industry or work in robotics labs. So, if you have any questions, you can answer.
When you showed the challenge course, what scale vehicles are you using?
So for the challenge itself, we've brought our prototype vehicle back here.
Okay.
So the challenge has its own limitations. The max size limitation is 4 by 7 feet.
Okay.
And they can be as small as 2 by 3 feet.
So you're working at a smaller scale.
This allows us to really work out all the algorithms and figure out sensors.
Okay.
Really cost effective, right?
So how did you get interested?
How did I get interested? I think freshman year, M-City was open, and I asked them if I could work there, and they said no. And, you know, for me, really, the best way I learned, I think, is by doing. So it kind of just was like, hey, let's try to find something we can do, and just go with it and see where it goes. Yes?
How would you take the one that just worked on the environment and make it autonomous vehicle?
So with that, I guess you could add some sensors on it. For example, we use LiDAR, so that's a sensor that shoots out laser and light and it detects how far things are. You could also add some other sensors like cameras. I'm sure you guys have an IMU in there, Ross. Yeah, so you can take all these sensors and really help to make it autonomous. You need to make it localize itself in the environment, figure out where it is, and figure out where it needs to go. So we will be adding sensors and some algorithms. I'll be answering. Thank you. So I think that's the last of our formal presentations. We do have some demos in the back. So the IGB team has a LiDAR set up here. So if you want to see what you look like in laser, I can go check that out. We have some more videos of Cassie from the outside. Feel free to go and take some pictures of Cassie. We also have the VR goggles, so people want to stick around and take a look at the new building that we just broke ground on. Come back and talk to us there.
Before we start to all play, because I know I want to use the virtual reality classes and see if I can navigate with that, I want you to join me in profusely thanking our robotics team for coming here to Ann Arbor, from Ann Arbor here to Lansing today. Thank you again.
you so much.
No, thank you. Appreciate it.
It's super interesting.
As we prepare to go and further experience this technology, I want to invite up Kirk Lutz from the UM Alumni Association with an announcement about our important event next week, the Michigan Alumni Reception in Lansing, which I know you'll all want to attend. So come on up, Kirk.
Thanks, Veronica. Good afternoon, everybody. As she said, next Tuesday at 5 o'clock at the Radisson just down the street, we'll be hosting our annual reception for alumni and legislators. Really would invite all of you to come out for that. Not only will Jessy and his team be at this event, but also President Schlissel will be giving remarks and talking about some other ways in which the university is really leading when it comes to innovation and technology. So if you'd like to attend, please see Valerie or Tamara at the registration table where you came in, and we'll get your name on the list. And please feel free to invite other alumni or friends that you have that you think would be interested in this sort of thing, and you can get a little closer and a little more info about Cassie Blue and how U of M is leading the nation in this important field. So thank you very much.
So on behalf of the UM Alumni Association and the Office of the Vice President for Government Relations, and Rebecca DeBlue is here, our State Relations Director for the University of Michigan, and all of the legislators who've come today to join us, thank you for being here, and we just want you to enjoy the technology. And we'll see you again in September when we talk about elections 2018. Have a good afternoon.
Thank you.